Nature is nonlinear. Nature is mechanics. Nature is composite. Nature is structured. In short, nature is the dance of nonlinear mechanics of composite structures. प्रकृति गैर रैखिक है, प्रकृति यांत्रिकी है, प्रकृति समग्र है, प्रकृति संरचित है। संक्षेप में प्रकृति समग्र संरचनाओं के गैर रैखिक यांत्रिकी का नृत्य है। भूमिमंगलम भूमिमंगलम उदकमंगलम उदकमंगलम अग्निमंगलम अग्निमंगलम वायुमंगलम वायुमंगलम गगनमंगलम गगनमंगलम सूर्यमंगलम सूर्यमंगलम चंद्रमंगलम चंद्रमंगलम जगतमंगलम जगतमंगलम जीवमंगलम जीवमंगलम देहमंगलम देहमंगलम मनोमंगलम मनोमंगलम आत्ममंगलम आत्ममंगलम भूमिमंगलम उदकमंगलम अग्निमंगलम वायुमंगलम गगनमंगलम सूर्यमंगलम चंद्रमंगलम जगतमंगलम जीवमंगलम देहमंगलम मनोमंगलम आत्ममंगलम सर्वमंगलम भवतु 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 सर्वमंगलम भवतु 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 सर्वमंगलम भवतु भवतु भवतु। ओम।
Very good morning, everybody. Are you able to see the slide?
Good morning, sir. Yes.
Thanks, Shravan. Let's go ahead. Today is the 7th class of our course. Oops. Today is the 7th class of our course, and we'll be looking at a little bit of the course information, of which you already have a preview. We'll talk a little bit more about it and some other upcoming events related to your paper submission. And then for most of today's class, we'll be looking at an overview of modeling composite materials, in particular how to obtain their nonlinear mechanical behavior. So what is the approach that we are going to take in this course? So we will look at certain aspects of that, and we'll also look at the existing current models and see what is the issue with them, because of which we need to go for new models. So one is, first of all, why should we model composites? That is one of the questions we'll try to answer. And then if we are convinced that we have to model composites and composite materials and structures, then what is the next step? What are the current available choices, and what are the issues with them, and therefore how we could probably overcome them with newer paradigm of modeling from what is currently the method used by most people, including the academia and the industry. So that is essentially what we will do, and we will also take a peek into what are the ingredients into that model, which will help us construct that model as we go forward in the next 1 or 2 weeks. So let's get going with that then. So the first thing is, as I already mentioned, what you see on the top right corner is not the way this grading is going to be, because unlike most courses where it's more exam oriented, competition oriented, here we are trying to do a little bit of value addition to our lives in general, and to our ability to do composite mechanics in a better way as part of our profession. So that is essentially the ultimate goal of this course. So that being the case, we will not have this kind of focus on the rat race, so to speak, because at the end of a rat race, even the winner remains a rat. So we do not want that kind of an approach, and that's essentially what we are focusing on, is the ability to perceive things as they are, which is essentially knowledge, and also the ability to put that knowledge to practice, which is why you have this research article assignment, where we are trying to look at how we can apply the knowledge that we are gaining as part of this course, as part of the self-study that you will do in parallel with the course, how you will put all of that together towards some kind of a value addition to the composite mechanics community in terms of better ability to solve such problems, whether it is in analysis, design, or various other aspects involved with it, or like optimization, health monitoring, and failure avoidance or failure analysis, and improvements in design of existing structures and so on. So that is essentially what we will do, which means that we have to be prepared to a 3-point agenda over here. The first point is something which is very significant, especially for this course, but it is kind of important in whatever new thing that you study, to come with, as I said, an open mind, recognizing that there is no box, which means that you have to. Okay, did somebody admit Kedar, who was knocking on the door at the lobby?
Yes, sir.
Okay, thank you very much. So welcome, Kedar. Where are you from?
Sir, I'm from IIT Bombay. I'm a
Okay.
senior PhD research fellow over there with
Okay.
Professor Guru Prasad as my advisor.
Wonderful. Yeah,
Yes,
glad
thank
to
you.
have you here, Kedar.
Yes. Thank you, sir.
Welcome. So let's continue. So as I said, one of the things that we need to be really prepared for in this particular course, unlike many other courses, is, but I would suggest that you take the same approach with other courses and other modes of learning as well, to be with in an open mind, recognizing that there's no box at all, so there's no question of being out of the box, but just that that freedom, which means that the first essential thing is the willingness to unlearn the not so correct. Because knowledge is basically a progression. It's not like I know it. It's a question of, this is my level of knowledge. I want to know more and more about it. Whether it is you, me, or Hodges or Berdichevsky or anybody else, even the rishis for that matter, are seers who are trying to look at more deeper and deeper aspects of the truth. So which means that we have to be willing to let go of what we have learned already, which we think is the ultimate, but there's no such thing as the ultimate. It's always a journey that we are progressing on. So which means that we might have to unlearn some of the not so correct. So to give you examples, the Timoshenko beam theory, or the Reisner-Mindlin plate or shell theory that some of you might have come across, or the higher order shear deformation theories associated either with beam-like structures or shell-like structures or plate-like structures. There are issues with them. Not that you don't use them at all, but once you recognize that there are better ways of doing it, as long as you are capable of doing that, you should move forward towards these new sets of knowledge. So that is the first step, unlearning the not so correct, and that is possible only through active listening. That is what we call as Shravana, and that's very, very critical over here. The next is to learn the more correct aspects, and which is what we will learn through the geometrically exact theories, both for the beam as well as for the shells, plate being a special case of that. And beam and plate together as combination in semi-monocoque constructions for aircraft structures, be it in the fuselage, in the wing, or the horizontal and vertical stabilizers, in the case of an aerospace engineers amongst you, but it could be the columns or beams that we have at our homes, or any buildings that you're designing or analyzing for the civil engineers, for the various machinery and automobiles and things like that for the mechanical engineers. But whatever your background, there are various possible potential applications, and the one that is immediately forthcoming is, of course, your manuscript that you're going to submit as part of this particular course. So learning that more so correct is the second very important thing, to understand what is the newness in that, and we will get a peek into that hopefully in today's class, time permitting. I'm, as you know, well known to extend the time beyond the class hours. So and the third thing that we will be doing is to enhance our ability to apply that assimilated knowledge, and we are doing all of these in parallel. It's not that I will finish unlearning all the not so correct, then only I will start learning the more so correct. No, it starts off, all three start off in parallel: Shravana, Manana, and Nitidhyasana. And that Nitidhyasana is the third thing, where you're trying to apply whatever you're learning as you learn to whatever problem you have chosen, and which is what is dictated by the titles that you have already given as a tentative title for your manuscript, that defines the problem or the application to which you want to apply this assimilated knowledge, not only from the lectures but your self-study, because that's also important, considering that we have a very short period of time, and that's why the bunch of 26 lectures that we have as part of the flight vehicle structures course, which most of you who are crediting this course have credited that also, so which is very a nice state to be in. But even those can go back to some of those lectures, especially the last few, 24, 25, 26, if not all of them, at least the 26th lecture, which is a 3-hour lecture, to get to speed with what you're actually getting into in terms of the new knowledge, and or the better understanding of things that what you already understood in a different way through your strength of material courses or elasticity theory courses, or any material science related courses which are associated with composites, and general analysis and design of composites courses. So how you can kind of upgrade yourself in terms of doing things better, and by better we mean, of course, one is accuracy, the other is the ability to do it faster, which means that you are enhancing your efficiency of modeling it, whether it is analytical or computational. If it's computational, how you can bring down the CPU times on the same computational hardware and software that you're working with, and finally, of course, in terms of bringing down the expenses, how much of effort you are investing in, as in terms of your human hours, how much you need to invest on that. It's not just the CPU time, but how much you invest on that. Are you becoming efficient at that as well? It should not become drudgery, never hard work, okay? Leave alone the hard work for donkeys, as I said earlier on, neither for you nor for your computers. Let's all try to do it in a more efficient way, in a way that incorporates the state of the art, not just for the sake of incorporating the state of the art. It's not like a fashion show that we are participating in here, that we just want the latest and to show off that latest thing. No, here we are trying to look at what is the new thing which can be of utility in attacking the problem that you have chosen, and how you can actually implement that. And a part of this will be visible in the Sankalpa, which is due this Friday. So as I already told you, you've already submitted the tentative title by last Friday. Thanks to all of you for meeting the deadlines. It's very important that we meet the deadlines for this, because otherwise, if we don't, then the next target gets affected as well. So because all these are quite close to each other, and many of you are first timers writing, almost all of you in fact are first timers writing a journal manuscript, and therefore there's a lot of learning that you do, not only from the point of view of the variational asymptotic method, the geometrically exact theories, but also in terms of the very concept of writing a technical paper. So this technical writing is very different, as I discussed in the previous class, from the regular writing that you might be used to, including the way you write your assignments or exams or whatever. So to get you up to speed on this, This Saturday, we will have a special class from 5 p.m. to 6 p.m. Hopefully, all of you can attend that because it's a very, very crucial thing. And the reason why it's put up on a Saturday is because Friday is this Friday is the due date for your draft abstracts. And March 19th being the by the midnight of this Friday, that's Friday, Saturday midnight, you would have submitted that. So at Saturday, as the Saturday dawns in, we will have all of your draft abstracts in place. So Kaja, Vinyas and I will be able to look through that this Saturday morning, that is on March 20th. And on March 20th evening itself at 5 p.m. we will have a special class where Vinyas will walk you through the typical process by which you approach a research problem, your specific research problem, and how you can go about getting at its solution in the way that you have described in your sankalpa or the abstract, and therefore how you can accomplish that using the tools or toolkits that you have as part of the course, as well as the self-studies that you're going to do in parallel with your textbook and related research papers in the International Journal of Nonlinear Mechanics, International Journal of Solids and Structures, Composite Structures, and related such journals, wherein you will find material related to these in the current state of the art, and also, of course, specific literature associated with your own individual applications, which will differ from individual to individual. So how you to take gather all of that information, how you organize it in an appropriate database, certain best practices in terms of how you can get well organized, and then put them all together in terms of extracting the information, conveying it in your own words in the short literature survey that you're going to write as part of your introduction to your paper, and then identify the research gap where the current state of the art is. As I mentioned in the previous class, don't ignore talking about the pioneering work in your fields, chosen areas as well. What were the initial breakthroughs, and what is the current state of the art, and what you can probably provide in doing things better, faster, and in a more inexpensive way. So that essentially is the introduction part, and then you will get going with the application and the solution process, and then eventually the documentation of that. As I said, as we mature, what is becoming more and more important is multimedia ways of expressing our research results. Many of the papers also require you to submit a typical video. It's an option for most journals today, but as we go forward, this will become an essential aspect for most journals, that because most people are of the fast food generation today. We want things in a quick way. So, and video is something that appeals to us through multiple senses, at least the eyes and the ears, and which means that the ability to gather information is much better, and the ability to convey it in a short duration is also very essential. So this is what you will do by your April 12th deadline of having to submit a 2-minute video. So the tentative title and draft abstract are the building blocks for which no marks are there as it is, because it's your choice of a problem and your sankalpa, how you want to approach it. We will tweak it a little bit this Saturday's evening's class, as well as we go forward. And as you know, both of these are tentative and draft. That is essential to understand that things can change, and that is pretty much the life of a researcher. We start off with something and could end up with something entirely different. So we should be open to that. Whatever is arriving in our way, in the open box kind of a scenario, even as we do our research as well. But at the same time, having this is kind of avoiding distractions and getting lost in the ocean of literature that is available. You have some kind of a focus because you have deadlines, and you have already chosen your title and abstract, and therefore moving towards that. And there are three ways in which you're going to express it. One is the video. The second one is in terms of conference-like presentation that you will give, a 30-minute talk a week after you submit your 2-minute video. And finally, of course, your manuscript on May the 19th. So all of these, as I have already told you, is the dates are so designed that they are at least a week before your course drop deadline. I think the April 19th is about a week before April 26th, which is the course drop deadline without having a mention in your transcripts, and May 26th is the deadline for dropping a course having a mention in your transcript. So essentially you will have a self-analysis in terms of understanding where you stand, so that you'll of course be constantly interacting with Kaja, Vinyas and me every week, at least once a week, if not more. And this is beyond the classes. It's not just the Monday, Wednesday class. So we'll typically have a Saturday or a Sunday when we can catch up on how each of you are progressing. In the beginning stages, maybe we'll have more of these as a common class, but later on it will be for each individual, because each of you will be working on very specific problems and may be facing very unique obstacles, and how to overcome them might not be of too much of interest to the others. So we will take it up on a case-by-case basis with each of you individuals as you progress. So take advantage of this hand-holding that you have. You have a batting coach, a bowling coach, and a fielding coach. So take advantage of all three of us and see how you can come out with a really awesome innings on debut, because it's a debut paper for all of you, like how Ishan Kishan in the second T20I performed against England, and the very debut he scored a 50 plus so fast. So make sure that you utilize all your resources that you're working with, the textbook, the paid journals that I mentioned, and the three of us. I will see as we go if the title and the also the abstract is in an area of great interest to one of the alumni of our lab, the NM cadets as I call them. We have very long umbilical cords for the lab, so we remain connected to many of them. And in fact, some of their students are part of this class as well, though they are from outside IISc and therefore as unregistered guests. But I'll put you in touch with some of their advisors as well, so to see if you can benefit from their expertise as well. So you have a lot of resources, utilize them. As I told in the very first class, we want the classes also to be highly interactive. So stop me whenever you want to ask your questions and or doubts or suggestions, and we can see how we can take care of those things. Then finally, you would have the finals on June the 2nd for 30%. It's a 3-hour exam from 9 to 12. And in this, whatever title you have chosen and whatever abstract you're going to submit by this Friday, we would like something to have an overlap to happen with the coursework. It should not be a completely independent manuscript that you're writing based on something that anyway you're doing and nothing associated with this course. So that's why I've very clearly mentioned that it should have certain aspects of nonlinear mechanics of composite structures for sure. You can utilize tools like the variational asymptotic method, geometrically exact theories, either for the beam or the shell, to showcase that this is something that is a new tool that you have learned, and therefore you're utilizing it for a right purpose to make a real difference. It's not an incremental improvement in what exists in the body of knowledge or area of research that you have chosen your title in, but makes a substantial improvement. So that's essentially what we want to showcase, and that's why it has to have that touch with what the main theme of this course is. So through this process, it's not just this paper which is a takeaway for you from this course or the grade that you get, but more so in terms of your professions, how you actually have enhanced your ability to apply that assimilated knowledge and also continue to remain open. So what you learn as part of this course may not remain the state of the art as you go forward. 5-10 years down the line, you might look at even better ways of doing things, and probably you are responsible for coming up with those new methodologies even better than what you learn from this course or the textbook. So that's essentially keeping yourself open is the main takeaway that you will have from this course, and the willingness to tackle any problem at hand in the best possible way, by which we mean in a way that is more applicable to wherever the solution is, in a faster way, and without having to invest too much of an effort either from the computer or from you. So this is all that we will be looking at over here. Are there any questions on this before we go to the next slide?
Sir, I have a question.
Yes, please go ahead. Yes, Nilesh?
Yeah. How the evaluation of the manuscript will be done?
So it will be very similar to a peer review process that most journals adopt, and peer reviewers will be chosen by me in the form of an editor for this, and we will have some of my colleagues and peers and some of the NM cadets, alumni, and many of my collaborators across the world, some of who have agreed to be a part of this process. So we will go through that process. So it's not that we are going to submit it to a journal right away on May 19th that you give the manuscript. It's not that May 19th or May 20th we are going to submit it to a journal. We will go through a peer review process ourselves, and that's how the grading also will be decided, that 40% towards the manuscript based on independent individual markings of all these experts in your particular areas. And then once that comes, I will be as the course instructor, it's my prerogative to analyze those evaluations and see if they are kind of appropriate, and based on that, a weighted average of all of those will be taken into account in arriving at the marks for your manuscript. But the bigger takeaway would be to incorporate all the suggestions which come as part of this review process to further improve your manuscript and submit it to an actual journal, typically the Composite Structures or IJNLM, the Nonlinear Mechanics Journal, or the International Journal of Solids and Structures, or Sounds and Vibration. And many of you are working on some very intricate special problems for which many other journals may also be suitable. Some high impact factor journal is what we will target for each of your manuscripts, taking it forward. Does that answer your question, Nilesh?
Yes, sir. Thank you, sir.
Welcome. Anybody else? Any questions? Okay, thank you. So let's get going into the motivation. In the very first class, I gave you a motivation of why composites, both from a technical, industrial, academic point of view on the one hand, as well as the financial point of view from what is it that the industry likes about the composite and its usage on various structures and how it's benefiting, especially the aerospace composite industry, but also various others in automobiles, in sporting goods, in civilian constructions. Of course, civil engineers came up with the steel reinforced concrete much before we all thought about using them on aircraft. But of course, aircraft, some of the initial aircraft used wood or clothing, which are also in some sense composites, the natural composites. So what we will be focusing on is to go beyond that. We are now convinced that yes, composites can make a huge difference for a lot of industries, and therefore there's a need for us researchers, whether in academia or in the industry, to work on this as part of the R&D to improve composites on the one hand and to improve their analysis and design on the other hand. Now, if you want to improve the analysis and design and make them more suitable, then obviously modeling comes into picture. So that's essentially what we are talking about over here. Yeah. So what we are talking about here is the motivation for that modeling. Why a mathematical model for composites? Why can't we just do a series of experiments, first of all fabrication and then testing, and use those results, which is also a very applicable method and a very useful and important method. But what is the role of modeling, so to speak, in general, and for structures in particular, and even more particularly for composite materials and structures? So that's essentially what we will look at for a few minutes. One is that, of course, it helps to shortlist the most promising candidates theoretically before embarking on an experimental program. Why? Because experimental programs are typically very expensive, relatively speaking, in the sense that not only in terms of the money involved in making things, buying the raw materials and making specimens to the required standards, and then appropriate testing and the equipment involved for the testing, if you don't have access to them, renting it out or buying it in some cases if it's a large project. So there's a huge investment, and also the time involved, which is even more important. It's not just the cost in terms of the rupees, but also in terms of the amount of time invested on it. Is usually for the same task, if it can be accomplished with a mathematical model, can be much faster, save you more time and save you more money, both the M's. So that's essentially what we are trying to look at. And by doing that, what we want to do is to shortlist a certain set of promising candidates. And promising candidates, we mean that there's so many design variables that are involved in a composite. The choice of the fiber, it could be just a single fiber or multiple fibers in a hybrid composite, or it could be a sandwich construction, in which case material for the core, but essentially the choice of the fiber, the choice of the matrix, then the volume fractions for each of them, then any additives that you're going to use along with them, and then a number of layers that you're going to have, the orientations of each one of those layers, and then you're looking at the ordering of those orientations. So theta 1 to theta 2, theta 3, and so on to theta n can be jumbled up, and they can behave entirely differently. So it's not just a choice of the angles, but also in what order you're going to place them, which is the laminate sequence, as we know. And then what is the overall thickness based on the ply thicknesses and the number of layers that you have. And of course, the overall shaping could have already been decided by your aerodynamic designers and various other things. And in terms of the constraints, you might also have a weight constraint because the aircraft designer might have told you this is the amount which is allocated to the overall structural weight, which you divide between the structural weight of the wing, structural weight of the fuselage, fuselage, structural weight of the horizontal tail and that of the vertical tail, and a few other structural components that might be missed out in this, like landing gear, etc. And then once that allocation is made, within that allocation for one half of the wing, what is the weight that you can spare for the skin, what is the weight you can spare for the spars, for the transverse stiffeners or ribs, and for the stringers, how many so once you have the number of the weight allocated for the stringers, how many stringers can you distribute that weight within? Either you can have stringers of larger cross section, smaller number, or you can have a larger number of smaller cross section stringers. So you can all these are part of the design decisions that you take. So instead of doing all of these in an experimental basis, which means that you have to construct so many specimens and you have to deal with so much of cost involved, especially in terms of time, leave alone the money as well, which is substantial. So it's kind of foolish to do that, especially when you have reliable models. So the question is whether you have that reliable model or not. If you don't have, then obviously this is the only way to go about it. And even if you have a reliable model, you cannot completely relegate the experimental testing. It's essential, but you can and you should be able to reduce the amount of investment in the experiments as far as possible. And that is possible if you can have a set of basket of optimal or close to optimal solutions for your particular application. I was discussing a design problem, but the same thing applies to an analysis problem also in a different sense, or to an optimization problem, health monitoring problem, whatever you might have. You typically have lesser number of situations to consider once you have gone through mathematical modeling and of course analyzed its results. That post-processing is very, very critical as well. It's not just that you run through the reliable computational model that you might have and then feel that everything is done. No, there is a lot of human intervention required in terms of extracting, even after the post-processing by the computer itself, in terms of the plots and various other visualizations that it can give you, how you can extract useful information in improving your design, improving your analysis, etc. Is something that you as structural engineers will be responsible for. But the main takeaway is that you instead of considering a very large number of samples, you are looking at a shortlisted set of samples that you need to push through for the next stage, which is actual physical testing, as opposed to a computational testing that you have already gone through. So what this means is there's a reduction in the dependence on experiments. We are never ever going to get rid of experiments completely. Maybe in very, very rare situations, but even there, the certifying agencies will not allow you because without some bit of experimental testing, they will not certify the component or a subsystem or a system, and eventually the aircraft or anything that that those components go into will not be certified. And certifying agencies are fairly strict, irrespective of which country you're in and whether it's a military or a civilian aircraft. Of course, they have different details of the standards, but essentially they want to ensure certain levels of safety and certain levels of acceptability in terms of how these things will work. In this context, we are planning also for a course in the near future on certification aspects of composites, so which will be very, very useful for all of you. And certification of composites is something that we academicians just skim through in courses like AE252 by Dr. Narayan Naik, or my own courses, this one 352, or for that matter 204, the flight vehicle structures, etc. We don't have a thorough course on certification, which is a very, very critical building block in for many of you who are either currently working on composites or will be working in the future as well in your professions. And for this, we'll be leveraging one of the experts from Boeing. He is a graduate of IIT Kanpur, IIT Bombay, taught in IIT Bombay for a while and has worked for 32 years in aerostructures of the Boeing company in Australia. And Dr. Professor Amar Garg. He is just retired, and he's offering his services on a voluntary basis, and we'll try to schedule along with him and see how he can contribute some value addition to many of you in this course, as well as other students who are working in composites who are not part of this course as well can benefit from his availability. So I'll see how we can include Shravan and a few others, Kedar, etc., who are from other institutions as well. Maybe he has even given such courses for other institutions. So maybe, Kedar, have you participated in Professor Dr. Amar Garg's course in IIT Bombay?
No, sir.
Okay.
I have been taught by Professor Naik.
Okay, wonderful. Yeah, a great friend of mine. Yeah, thanks. So we will see how we can probably include some of you as well into this because it will be very useful as part of your careers. Because we, as academicians, we have a lot of freedom in what we want to work on in terms of the choices, the design choices we make. But some of those design choices may not be acceptable to the certifying agencies. So right away it reduces the design space or the domain in which we are working, and therefore within that we then do a modeling to understand further shortlisting for the experimentation. But essentially what it has led to, if we have a reliable model, is in terms of reducing the dependence on experiments, which in turn implies, as I already hinted earlier to you, reduction in the development cost, that is rupee cost, and as well as the time involved, which is even more significant, especially in industries like aerospace, where we are willing to pay a little more money if there is a performance improvement. So per incremental performance improvement, the amount of willingness to share enhance the budget is usually a little more in the aerospace industry compared to many other industries. It's also more in the F1 racing industry or some of the professional sporting industry products as well. So what is more critical for them is, are you able to achieve this in time? So either it is for these cutting edge industries that I just mentioned, or for the regular industries where cost plays a much more important role than even time. In either case, you are getting both these advantages simultaneously through this particular approach of theoretical shortlisting before we get on to experimental verification, validations of that, the testing to get more detailed results as well, more reliable results maybe. So that is the advantage, which means that if we are bringing down the development cost and the development time, we are also bringing down the overall product cost in terms of the overall cost of an aircraft, because the airline is eventually going to buy this, and the passengers are going to buy the tickets from the airline. So if we have reduced the cost of a structure, it is a trickling down effect that the cost of the aircraft to the airline reduces, and therefore the airline over a period of time can bring down the costs of the passenger tickets as well. This may not look very direct, but or even the amount of investment they have on fuels, because you have by bringing in a composite into a structure instead of a metal, just because of the ability to do a more reliable modeling in a much faster way, and therefore taking this composite aircraft to the market much more faster. In fact, you would be looking at in the course that I just mentioned of Professor Amar Garg, the Boeing 787. I forgot to bring that model with me here, but it's a very similar to the A350 in terms of its utilization of almost 50% by weight of composites, and therefore you would see that he would be talking about the Boeing 787's certification, especially for the composite components of the wing and the fuselage, which I think will be a great value addition, not only for you students, but even for us faculty members like me. So here we are talking about bringing down that overall product cost and more importantly, in speeding up their application in actual real life structures which are going to be marketed. So this trickling down effect eventually reaches the consumer. That's what is the example that I wanted to point out to you. So in terms of the affordability of flights, either for passenger or for cargo, whatever it might be, or military applications, you would be able to trickle down this effect. So you are in some sense contributing towards the overall improvement in the economy. So you have to understand how you fit into this overall process so that your motivation to do what you do is even higher. It's not a standalone effort that you're going to do. Not everything will eventually trickle down to the end consumer. You are working on, let's say, 100 different things. Maybe one or two of those will trickle down, but that's well and good, rather than not being of any significance to the society and humanity and the globe at all. So you are basically trying to achieve that, and which is what this can help. Finally, it helps produce closer to optimal solutions for the intended application. So what you already have certain applications in mind, but there might also come up new applications which you didn't even have in mind, but just because it came up, then you see how it can be applied. For example, some of the composites that DRDO developed, Dr. Abdul Kalam is said to have seen their applicability in medical applications in terms of artificial limbs, etc. And therefore, in terms of reducing the weight for physically challenged people, Divyangs, in terms of the replacements being much lighter and therefore much easier for them to utilize. So there are spin-offs, and in particular the aerospace industry, we can be really proud, has contributed to a huge amount of spin-offs to various other fields, unthinkable when those things were initially being worked upon. So many people crib about the amount of money we spend on the military and the aerospace industry in particular, but there have been so many spin-offs to various other industries which have never been taken into account in a holistic sense, in terms of how we've been contributing to other sectors as well. Of course, it's an indirect way of doing it. There could be better direct ways of doing it, better ways of spending the money. Well and good. In those cases, the decision has to be taken that way. But we should not be blind to the fact that, yes, there is a possibility that certain cutting-edge materials, cutting-edge design philosophies, cutting-edge geometrical arrangements of these structures, etc., can come out of aerospace into various other common structures that are of even more mass appeal. And of course, flight itself is becoming more and more of a mass appeal with airports in smaller towns and the Udan scheme, wherein the costs come down at least for a few people, and the ability to fly, even for those with Hawaii chappals, with Hawaii jahaz, as they say. So the ability to do all of that is increasing as well. And the introduction of lighter materials like what we do, and therefore bringing down the fuel consumption, and therefore the running expenses for airlines, the composites have played a big role in that, and will continue to do so if we can further reduce the cost of the composite. The cost of the composite is not just in terms of the material, but also the overall design process. So if we can speed up that design process, reduce the cost by reducing the experiments and with reliable models, then obviously you have a win-win situation for the entire ecosystem, the aerospace ecosystem, as well as the end users. So we get closer to optimal solutions. So in other words, just by applying that theoretical model in a repeated fashion, in an iterative fashion, you are coming up with optimized solutions or near to optimal solutions, a certain basket that you have come up with through this short list, and only on that basket short list we perform these experiments, and therefore we are saving on the cost, the time, and we are getting to the market very quickly. Go to market is time is shortened, and we are going to that with far more optimal solutions as well. In other words, you are getting better bang for the buck and better bang for the time invested or the human resources invested or human potential invested as well. Anytime feel free to stop me and ask questions if you want. So that's now we have understood in the very first lecture of this course why composites. So in the lecture today so far we have understood why modeling composites. Now that we understand that yes, we need composites, we need models for composites, what is the need for new models? So that's essentially what we are trying to look at in this slide. What is the need? Why can't we use the existing models? There are many models and which have existed for a long period of time. Some of them as generalizations of the approach taken for metals by introducing the new complications of heterogeneity, that is properties varying from point to point because of the existence of multiple materials at a macro scale, namely your fiber and matrix to start with, and many other additives or voids that you might have, and then you have all of these kinds of situations. So why do we really need these new models in spite of having that kind of already existing models which are taken care of the heterogeneity and the anisotropy, the properties varying at a point in different directions. So there are ways of handling that. So then people have tried to extend the theories for isotropic materials to anisotropic materials, for the homogeneous materials to the heterogeneous materials, and therefore whatever was applied for let's say aluminum alloys which were used to build some of the older aircraft, now how you can utilize them for analyzing some of the newer aircraft as well, like the A350 which are made more out of composites, etc. So that learning process has continually happened. So what are the issues we have to see? And this is again on similar lines of thought you will develop your paper as well. Once you have written your title and the abstract, you will look at literature survey, which will tell you what are all the existing models, what are all the existing approaches to solve that problem, and what are all their advantages. Of course, they had advantages, which is why they are in use, but what are their potential regions where or domains where you can make improvements, and that's where that research gap is identified, and how you with your new tools can address those research gaps and make things better, faster and cheaper is what this whole thing is about. So this whole thought process that I'm taking you through in this class will be applicable to your specific problems also. So see the parallel as I'm talking about this, see how it applies to your specific problem. So I want you to continually think in parallel. They say focus is very important, but focus again is for the unintelligent, where you are capable of only looking at one thing at a time. If computers are capable of parallel processing, doing multiple things at a time, why not human beings, one of the most sophisticated machines in terms of our intelligence? We are capable of doing things in parallel. So I would like you, as you listen actively to what I am teaching you, also to think of how it applies to your chosen title and the abstract that you're writing, and how you want to take it forward. So that's why when you do the literature survey, you will look at all the old models, and then you will build up a case. Just like a lawyer is building up a case for his or her client. Similarly, your client is your approach to solving this problem, which you think is a better approach. Is it really better? First of all, you need to be convinced before you can write a paper and convince somebody else. If you are not convinced in the first place, then you can give up on the hope of convincing others about it. As they say, you can fool all the people for some time, you can people some of the people for all the time, but you can't fool all the people for all the time. So you have to first be strong in your conviction, yes, this is useful, and then of course run it through us, your mentors, to make sure that yes, it's not something you're getting carried away because it's your baby. They say for the crow, even its child is the most beautiful bird that can ever be. So your own creation, your own research, your own paper, manuscript might look awesome to you, but as mentors who have a little bit more experience than you, we can probably come out and show some of the shortcomings in that, not from a sense of fault finding. That's not our goal, but our goal is to improve your contribution even more, improve your whatever research you have done, how to improve that, still within keeping that time limits in mind. You can't go overboard in terms of improvements. Keep something for other papers in the future as well. But so that is one thing that we are trying to do as part of this whole process, is to handhold and walk with you. But essentially it is your baby and it is your work, and you are responsible for it. All that we can do, just like in the cricket team, the coaches are not part of the playing 11. The coaches are just encouraging you, identifying certain ways in which you can improve and probably perform better in the next thing that you do as part of this overall process. So think of this as a series where you have multiple items, all that thing that we talked about in terms of the title, the abstract, the video, the presentation, and the paper, as all is a 5-match series, and you're slowly becoming better and better. The whole idea is to win the overall series, and that's essentially what you're trying to do, and we'll try to help you out with that. So now let's look at what are the reasons why we need to look at new models. What is the issue with the existing model? So think on the same line to identify the research gaps for each of your individual papers. Now let's look at this. First of all, there has to be some issue with the existing models. If the existing things are working well and good, they are already better, they're already doing an amazing job in terms of their accuracies, in terms of their speeds, then there's no point in with just for some incremental improvement coming up with something new just for the heck of coming up with something new. No, we have to identify a certain issue, and if we should have the courage to drop a problem and take up a new problem in case we find that we are not going to make a huge difference to that at all. Okay, so you have to get convinced, yes, there are issues with the existing methodologies, which means that you have to look at all the state of the art, which is why as important as it is to look at the pioneering work, creating breakthroughs a few decades ago in your problem, it's equally important to look at the state of the art in the last few months or the last couple of years, what has been done in your chosen problem area, to know what is the current practice. Of course, again, we may not know the current thing because many of them are confidential within the industry, but whatever is available in the open literature. So, and which usually takes a little bit of time to publish, because by the time you submit a paper and it goes through the review process and you make the changes according to whatever the reviewers asked you or the editor asked you, and then you resubmit and eventually it gets accepted, there are a few months which lapse, and therefore you always find it a little older. But conference papers are usually a little more faster at giving you the current state of the art in terms of people working on something at that point of time and coming and talking to you about it. Directly you're getting what is the current state of the art, unless of course they're not revealing all of what they are doing because they want to keep certain things under wraps before it gets fully published. But whatever is available in the open literature in terms of your you have amazing JD Tata library where you have access to all the current journals and the old journals online, and therefore you can and of course the search tools are so easy these days in terms of searching for things relevant to your area of research by identifying certain keywords. So that's very important. As part of this abstract, along with the abstract, submit a few keywords as well. Okay, so because that keywords will help you in a lot of these searches and identifying the appropriate literature which you can then survey and then look at the current state of the art and what you can contribute. So coming back, one of the things, once you have shortlisted those literature which are relevant to your work from various aspects, then you look at amongst the current state of the art papers in the last few years, what is their accuracy levels. Is there a possibility of you improving their accuracies? Why? Because they might have made certain wrong assumptions, or they might have come up at a time when the computational capabilities were not good enough to handle the kind of theoretical rigor. So they made certain assumptions to take care of that. Or they were applying it to simpler kind of composites, which were probably the only things that were being looked at for applications at that point of time. We are looking at even more modernized versions of composites for applicability now. So there's a whole body of research going on in materials science in terms of improving these materials, and therefore they're better and better materials. Instead of unifunctional materials, you have multifunctional materials and so on. So whatever that is, but for the problem at hand, how are the others approaching it? If at all there are a few approaches to it, what are their accuracy levels? So can you identify that there is a certain lack in the accuracy levels? So there is a potential to improve their accuracy. So that is the insufficient accuracy of the old models. That becomes one of the primary reasons why you want to go for a new model for anything, but in particular we are focusing on new models for composite structures. Then there's a need to change or shuffle across old models even for minor changes. Like for example, you have two beam theories, let's say Euler-Bernoulli beam theory and Timoshenko theory. Later on we will see that the Euler-Bernoulli beam theory is an asymptotically correct theory at its level. Timoshenko theory is a refined theory, but it is not asymptotically correct, and that's why you have issues, and therefore you have to apply shear correction factors, etc. So now just by having these two models, they can't apply just the Timoshenko model for all the problems, even though it's a more refined model compared to the Euler-Bernoulli beam problem. So they will keep shifting between this and that. So there is a need to change or shuffle across the old models, even for some small minor changes in the design, small change in the material and or the geometry, you have to go for an entirely new model. The old model that you are using for the old design may not be applicable. So then also you want to see if you can generalize that. Can you make your model a little more generic, so that it applies? Still, it will not apply to all problems, obviously, but can it apply to, instead of a small class of problems, can it apply to a bigger class of problems, of which that smaller class was a subset? So enhancing the range of applicability of your new approach is also another reason why you would want to do it in a different way, and therefore a new model, so to speak. Then the third reason why you would want to get onto new models is the identification of certain issues in terms of the mathematics, in terms of the physics involved over there. So in applying physics and math to the problem, because of its complication or because just because of ignorance, people might have used what are known as ad hoc assumptions. What are ad hoc assumptions? They are valid for that particular problem that the author might have tackled. So the solution is there's nothing wrong with the solution, but because it was an assumption which is valid only for that specific problem, we can't apply that same approach as it is for any other problem which might be somewhat similar to that old problem, but just because the assumption that they made is no longer applicable. So that narrow range of the validity of the assumptions that some people make, we need to see if we can go beyond that. It may again not be always possible. You might have to make certain specific assumptions for certain situations, but in many cases where it is possible, can we give up on those so-called specific assumptions or ad hoc assumptions and still march forward? And that's again the way we can enhance the range of applicability of our problem, of our solutions, or the approach as well, the algorithm. Then sometimes it is specific, and sometimes even worse, it is invalid. And many of these unfortunately have got published also. It's just because something is published and you see that in a book being published by a great renowned publisher, or it is in a journal which is of high impact factor journal, doesn't necessarily mean that it is the Bible or Quran or the Gita for you. No, you have to look through it and see if there are things that can be done better, because that's how science has developed. You don't consider anything as a conclusion or a ultimate, even if it is by great people, even the people whom I consider great, like Hodges or Berdichevsky or even myself. Whatever is the contribution that we have made, there is a possibility that things can be better done than that. There are certain things which could be further enlarged in scope by reducing the number of assumptions that are there, and sometimes we might have even made invalid assumptions unknowingly. So are there ways that once we identify that, are we having the courage to correct that and move forward? That is the question, and I think we should always be open to that. Again, that open being in recognizing that there's no box that you're in is very, very important in doing that, because you're not so concerned about in fact, you should be the best fault finders of yourself. Before anybody else points out to some issue either in you or in your work, you should be able to do that, so that you can have a jump start in terms of correcting it and making yourself better. That is the whole purpose of growth as a professional, growth as an individual. So we will try to see in the existing old models for each one of your chosen problem areas, are there certain assumptions that we can give up, which others have made, which were specific to their problems, and therefore enlarge the scope of their problem. Second, can we identify, even if it's from some big names, there are certain, of course, don't just jump to a conclusion, yes, this is wrong. Okay, you have to prove that it is wrong, and it's not just because it's of some reputed person, or even of a newbie like you. If you have published a paper, there is a possibility that it is actually a valid assumption, and an expert like me comes and points out, yeah, there is a problem. You should be willing to see through it from an open mind and say, if there is really a genuine problem, yes, I'll try to correct it. But if it's a problem that the reviewer, in spite of all his experience, is not able to see through it, then you try to convince him. That is how the response process works. Since most of you are, all of you are writing a first time journal article, except for one or two, so I would some of the things that I mentioned might look a little overboard for those who are already experienced in it, but even you can actually improve by taking these approaches in mind. So because the review process, the reviewer, sometimes the reviewers might be critical just for the heck of being critical, or there might be certain subjective criticisms also. You have to be able to see through it and able to defend that. But more often than not, the choice of reviewers, you can say who not to be chosen as a reviewer, your suggestion, whether the editor accepts your suggestion or not, it's up to him or her. And similarly, you can suggest a few reviewers. Whether the editor chooses them, again, is their prerogative. But essentially, you have certain control over this. And once the reviews come to you, then you have to see in that that review, there could be definitely at least one or two constructive reviews, and some of the suggestions are more often than not made to genuinely try to improve your work, or it's the way it is communicated, without having to do any new work for the work that you've already done, how to kind of improvise that. So we will continue with all that process even after this course, with all those of you who are crediting this course and who have submitted the manuscripts to us by May 19th. We will take it forward and walk you through with all of those review processes, and when the reviews come, the responses that you write for each one of those questions, to see if we can enhance your response to make it more convincing to the reviewer, etc. But essentially, there is a possibility that you have made a valid assumption and the reviewer is pointing out that it is invalid. Then you, if after having gone through it with an open mind and seeing yes, it is really valid, then can you build up a defense to say yes, this is really a valid assumption and this is the reason why it is valid, and try to be more convincing than what you have already been in your paper. So if you know all of these thought processes of reviewers early on, you will try to preempt that. When you submit your first manuscript itself, you make sure that yes, this is possibly a weak point where a reviewer might come in and say something like this. Can I present it in a way, in a more convincing way, that I can preempt that or avoid that reviewer coming up with that comment in the first place. So that's the way that you have to think. Always when you write a paper and then read it after writing your first draft, and then read it even before you submit it to any three of us, you have to read it from the point of view of you being the editor or you being the reviewer and reading somebody else's paper and trying to find issues with it and see if there are ways in which you can be more convincing and therefore to avoid that. So put yourself in the shoes of the editors or the reviewers or your mentors and see that most of the changes are made by you already, and then that whole process will help you to be more stronger in your conviction and help you to defend when anything that you have not foreseen, that this reviewer might come up with some kind of a suggestion or criticism that you have not foreseen. You'll still be ready because you have gone through this process, being the best critique of yourself. So it's different. Criticism is different and critique is different, and critique is usually something which is trying to help you improve, and from that point of view always read your paper not as an author but as a reviewer, even though you have written it. So this is the third reason why we would want to go for new models. That is essentially because the assumptions are either invalid or too specific to a problem, and therefore you want to generalize it. So those are the issues. And the fourth issue that some of the existing methodologies could have is in terms of their empirical nature. So they might take certain factors based on experimental results or through, let's say, a Monte Carlo simulation kind of approach where you're repeatedly running for various random samples and then coming up with certain empirical numbers, etc. So can you, because empirical is again, it's just the trick that we used to play to fool our teachers probably in school, just that you didn't get a graph the way it was supposed to be obtained, and so but you still drew it that way and passed it off as a result. So these kinds of things get easily found out in this kind of a strong peer review process more often than not. So you have to be a little more better than just doing a curve fitting. And this curve fitting is what these people who are doing empirical models are doing. For some problems, yes, you cannot do something from a fundamental mathematical and physics basis, and empirical is the only best possible way to go for it. But where there is already an improvement in the understanding of the science behind your problem, improvement in the mathematical tools to solve those mathematical models in a probably exact solution or asymptotically correct solution. So wherever there is a feasibility to give up on these empirics, we have to. Just like in the previous slide, we saw Y modeling. If we can give up on some of the experiments and take theory to its maximum applicability, it's good. But again, here we are trying to see that within theories there can be empirical theories, which is again no good. It again could lead to this problem of being specific, and you need to get those empirical coefficients for a new set of materials or a new set of geometries, combinations, and it's a time-consuming process. So the whole purpose of getting to a good theory was to get to avoid some of these experiments. But if it's going to be an empirical theory that you're developing, to get the empirical coefficients, you have to perform a series of experiments. See, so you have to see wherever it is feasible. In many cases, it may not be, but wherever it is feasible, can we get rid of these empirical coefficients? And you'll see a very classic example of that in our course, where we will get rid of the Timoshenko theory by a geometrically exact Timoshenko-like theory, where we can give up on those shear correction factors, which is again an empirical number. Similarly, the Reisner-Mindlin plate theory, which is one order superior, said to be one order superior to the Kirchhoff classical laminated plate theory or a classical plate theory. Again, there you need these shear correction factors. I'm telling shear correction factor because that's one example that some of you might be aware of. But there are many such situations where empirics is very commonly used and can be avoided, especially in the design processes. If you look at most industries are just bent on doing it that way because that's the way which has worked for them. But once you give a proper convincing demonstration of a better way of doing it, they're more than willing to take it up. Just that we have not done our due diligence as academicians or as researchers in convincing the other party, yes, there is a better way of doing it, and in the long run it might help you. In the short run, yes, it's an investment of additional learning efforts on part of your engineers or your managers. But once it is done for the longer period, it will really help. And most visionary companies which are there for the longer term than just trying to make a fast buck today and vanish tomorrow, most companies are not like that. Especially in the aerospace industry, you need to have a long gestation period before you can make profits. Even if companies, leave alone aerospace, companies like Amazon or Flipkart don't make profits for a very long period of time before they can be sustainable or self-sustained. So you have to see, is there a better way of doing that, and the ability to sustain yourself. And most aerospace companies are able to look at that kind of a thing which has a longer term advantage, even if it means a little more time and effort investment on part of their human resources right now. So that is the other thing that you can try to find when you do a literature survey on your specific problem. Try to see if some of them are using empirical models, and see if your approach can avoid that. So that is one way of seeing that there is a research gap, and I can contribute towards filling that research gap, making it better. So that is one thing. After this slide I will stop. So no, I think we still have time. So non-classical nonlinear phenomena which are observed in reality. I'm still continuing. This is the fifth reason why we would want new models. So the fifth reason why we would want new models is something has not actually been observed, but might be an existing issue. And some things can be observed and is already an issue. Whatever it is, these things are not captured by the so-called classical theories. That is, the theories which were the very first pioneering theories with the simplest model that you can have, made with lots of assumptions, so many of which could be invalid, some of which could be ad hoc. But essentially those are the classical theories which have been used substantially, but in spite of knowing that there are issues with it, just because it's easy to use. It's just because it works for some special cases. cases, or it gives you a first cut result using which ballpark values you can work around through number crunching into a better way. It gives you, let's say, for an iterative scheme, it gives you the first solution with which you start the iteration. So that is the initiation, what we call. So that for the sake of initiation or whatever. So, but they are classical theories. But those classical theories, typically linear models, will not capture a lot of phenomena. So are there certain phenomena that you observe that in your literature survey for your specific area of the paper that you're writing, whatever literature you have collected, are some of them not looking at certain phenomena which might actually be important just because they are not classical or linear? Can you bring in this non-aspect over here, this negative aspect over here, to say that I can broaden the horizon from linearity to non-linearity, from the classicality to the non-classicality, and therefore be able to capture certain phenomena which are actually observed in reality, be it in an actual flight test of an aircraft or a helicopter or a satellite vehicle, or it could be in a bridge or an automobile, whatever it is, but it is seen, actually seen and observed in reality, either by the naked eye or through sensors which capture the data of the behavior of these structural materials. So these are phenomena which are observed in such way, but it's not captured by your linear and classical theories, which are the old models. And therefore there is a possibility of you jumping in and giving a value addition to that entire body of knowledge, to that entire set of peers who are working in that area, to see how you can enhance their toolkits. So next is the sixth reason why you would want to go for a new model for composite structures, which is the low reliability of the old models. And reliability, I have already told you, is two-pronged, at least two-pronged. One is accuracy, the other is efficiency. Very accurate models which are inefficient, and very efficient models which are inaccurate. So you want to go through what is the level of accuracy which is demanded in that application. In a preliminary design, you may not demand that much of an accuracy. In a detailed design, you will demand a level of accuracy. In an accident investigation or failure analysis or opportunities to improve the design, you might look for even more reliable models. So even more accurate models. And in all of these, if you want to do it in an iterative sense, or you want to apply it in a repeated way, you would want to look at the efficiency as well. And many of these might be real-time applications like structural health monitoring, about which I talked in a little more detail earlier in an earlier lecture. So in all those cases, you recognize either it is inaccurate, the old model, or the old model is inefficient, or both, which is the worst case scenario. And therefore, can you come up with a new model which makes the model more reliable? And therefore, people who are going through experiment after experiment, spending money, spending time, spending human resources, can they be benefiting from this and take the product quicker to the market? So that is another reason why you would want to look for new models, is the low reliability of the existing models. So coming from all of these six reasons that we have had over here, one is the insufficient accuracy, the second is the need to shuffle across old models, the third is the invalidity or specific nature of assumptions, the fourth is the empirical nature of some of the models, the fifth is the classical and linear models not taking into account certain phenomena which are actually observed in reality. And once you bring in the actual non-classical, non-linear phenomena, you might be able to capture certain phenomena which are not even observed in reality but might be observed in the future. Just that people have been having a blind eye to some of these phenomena which are actually happening, but in spite of all the humongous sensor data, you are not doing appropriate post-processing and inference of that post-processed data to arrive at the recognition of those non-classical phenomena, non-linear phenomena, or non-classical non-linear phenomena. So in such situations also it helps in a futuristic sense. So it's not only the observed issues which are not captured by existing models, but also the unobserved issues which the existing models may not be capturing. So there's an unknown problem which is sitting. It's like a cancerous cell that might be, or cancerous tissue that might be there in my body, and I may not be even aware of it. So just because I'm not aware of it, having a technique to improve cancer is not going to be useless to me. It could be useful to me just because sometime in the future I might discover that cancerous tissue which is already there in me right now, but I don't know about it. So in spite of all the diagnostics that might be done. So that is essentially what we are trying to look at here in terms of moving forward from linearity and classicality to non-linearity and non-classicality. And finally, in terms of enhancing the reliabilities of the existing models. So from all of these points of view, our goal is therefore going to be to illustrate that potential of the new model. And this is exactly what you're going to do at the end of your introduction section and the beginning of your section on how you're going to start solving your problem. So you've already defined the problem through the title, the abstract. In the introduction, you have looked at the pioneering work, what is the current state of the art, what are the issues with each one of them from each one of these 6 perspectives. Once you have seen those issues, what is it that you can do better than that? And therefore you have identified the research gap, and you've also identified how to fill that research gap with your work. And therefore the first step that you have already accomplished in the introduction itself is the illustration of the potential of your new model. And in fact, of course, the abstract also gives that out in a very, very summarized fashion, in a very succinct fashion, what we call as in the Indian scriptures as the sutras, be it the Brahma Sutras or any other sutras, Patanjali's, Maharishi's Yoga Sutra. These are all very crisp and compact statements of the ultimate truth without building a lot of colorful words around them and building a mountain out of a molehill. No, you give it as crisply as possible. That's what your Sankalpa, which is due this Friday, will do. Very clearly and crisply state, this is the problem which my title talks about, and this is the way I'm going to approach it. This is the value addition that I foresee, but it is draft, and therefore I can change it, come back and change it later if I want to. So in doing that, you're illustrating the potential of your new model, because you know certain things about what we can accomplish through a non-linear model, through a non-classical model, by applying an asymptotically correct modeling, by using geometrically exact theories. So there are so many things that we can accomplish, but if you have to first of all find there are certain issues with the existing models, and therefore the goal here is to illustrate that potential of the new model that you are planning to develop. You have not even developed yet, but you are planning to develop, and therefore you have convincing yourself first of all, yes, there is going to be some potential in doing it. Otherwise, why the hell do it? There's no point in wasting your time. You could spend it in much better ways. There is no shortage of options to spend our time. So if we are willing to invest our time and effort into something, we should see the value in doing that. What is the potential of the new modeling approach that I'm taking? And that's essentially what you will do as the goal over here. Which means that in this course, what I will be doing in parallel to you working on your papers over there is to give you certain sample cases from around the world in terms of the modeling techniques in general for all composite structures, not for your specific problems, which is your job. You have to do that. I'll be looking at and sharing with you as part of these lectures the various advances that have taken place through these new approaches, potential new approaches of geometrical exactness, fully intrinsic formulations. You got some of the exposure to it in the very last class of flight vehicle structures, the 26th lecture. So those of you who have forgotten that or have not seen it at all, please once again I urge you to go back to that lecture and go through it and understand what fully intrinsic means, what geometrical exactness means. These are all terms that will come in handy in terms of selling your essentially it's you're a salesperson or a marketeer over here. You're doing something and you're trying to convince the world that this is something useful. Why don't you also utilize it if you are in the same field, or you plan to be in the same field sometime down the line. So to be able to do that, you have to first convince yourself, and in doing all of that, you should know what you're actually trying to accomplish. And that's where we will look at certain examples of others who have done these things, applying asymptotically correct theories, applying geometrically exact theories or fully intrinsic theories, and what is the advantage they have got out of it. So that is the we will look at a sample of that. We'll not go into too much of detail because each one of them is a huge body of knowledge and will go for hours on end in terms of the lectures, because the amount of human resources or potential which have been invested on each one of them. So but nonetheless, we'll try to illustrate some detailed studies that I have done at Georgia Tech, or my students have done at NMCAD lab. That is the past students, not the current students who are still doing their work, but some of the past students, what is the kind of work that they have done. If we can have some lessons from that, which we can look at in a little more detailed fashion, as opposed to just sampling them from others' work, because we know our work much better, and therefore can we give you certain leads in terms of understanding or motivation in terms of seeing how useful these kinds of applications of geometrically exact theories, of all these fully intrinsic formulations and or the asymptotically correct formulations, how they have been. Because in certain areas where you can do an exact solution also, that is where the geometrical exactness of the larger dimensions comes in. In other words, the 1D analysis for a beam, or a plate analysis, that is the 2D analysis for a plate or shell-like structure, can be done in almost an exact way, more so for the beam than for the plate or the shell. But and also we can take it to fully intrinsic formulation, etc. But there are certain things like the constitutive law. The 3D constitutive law, though in some special cases today it's being determined through molecular dynamics, etc. More often than not, it's the experimental results which gives you the Young's moduli in different directions, the shear moduli in different directions, the Poisson's ratios in different directions, and then the various other types of normal shear couplings in various directions. So most of these are determined in an experimental way. Then in going from the 3D constitutive law to plate or shells 2D constitutive law, or beams 1D constitutive law, there you cannot get an exact solution because you are doing a dimensional reduction. You can never get an exact solution. So what you have to understand is what is the next best, and therefore the asymptotically correct solution. So therefore you can improve it as much as you want to, but without spending too much of a computational effort, too much of a mathematical effort if it's an analytical problem, whatever it is, but essentially you are reducing the overall effort. So that is the overall process that we have to take. So you have seen in the first lecture why composites. In the beginning of today's class, the first half, you saw why model composites, and now in this slide you have seen why these new models for composites, and all of this is in parallel to your task towards that 70% of the marks. But more important than the mark is the learning process and of course the unlearning process of the not so correct. So thank you very much. With this I will end today's class, and as always, for those of you who can wait beyond this time, feel free to ask me any questions. I'd be happy to share my insights into them, whatever little I might have. Thank you.
मृत्युञ्जयमन्त्राः
त्र्यम्बकं यजामहे सुगन्धिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षीयमामृतात् ये ते सहस्रमयुतं पाशा मृत्योर्मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वान् वयजामहे मृत्यवे स्वाहा मृत्यवे स्वाहा